Hello and welcome to today's Safety and Health webcast, Weld Fume Management, sponsored by Miller Electric and Hobart Brothers Company. My name is Kyle Morrison. I'm the Senior Associate Editor with Safety and Health magazine, and I'll be moderating today's session. Thank you for joining us. We'll start the presentation in a few minutes, but first I want to go over a few housekeeping items. The views of the speakers and their organizations are their own and do not necessarily reflect those of the National Safety Council or Safety and Health magazine. Mention of any commercial enterprise, product, or publication does not mean the Council or the magazine endorse them. At the end of today's webcast, we'll have a question and answer session. To ask a question, simply type it in the text box located in the lower left-hand corner of your screen, then click the Submit Question button. You can ask your question at any point during the presentation. You don't have to wait for the Q&A session to begin. We'll try to answer as many questions as we can, but due to the large number of participants today, not all of the questions may be answered. However, all of the unanswered questions will be forwarded on to today's speakers. For basic troubleshooting information, please click the Help button located on your screen. At the end of today's webcast, you'll be asked to complete an evaluation survey, and I'll talk a little bit more about that after the presentation. This webcast will be archived for 3 months, so you can access it after today's live presentation. Within about a day, just simply return to the same URL to access the webcast. Okay, with that, I think we're ready to begin. We have 4 speakers with us today. Bert Schiller is a certified industrial hygienist with Bert Schiller & Associates with more than 35 years experience in a variety of industries. Al Hilbert has more than 23 years of experience in the welding industry and is currently a fume extraction product manager with Miller Electric. Stephanie Lowney is a respiratory product specialist with Miller Electric, where she is responsible for respiratory development in the company's Arc Armor welding production line. And Aaron Bischoff is a weld engineer with Hobart Brothers Company with experience in developing and implementing welding processes. Aaron?
Alrighty. Well, we'd like everyone to be aware that every welding environment is different and needs to be evaluated by a qualified industrial hygienist to determine the appropriate course of action for fume controls. This presentation is intended for awareness and educational purposes only and should not be used to replace professional consultation. No express or implied warranties of any kind are provided with this presentation. And now I'll kick this off with Bert Schiller providing a little bit of background information on Weld Fume.
Thanks a lot, Aaron. Potential air contaminants generated from welding consist of a mix of fine particulates, metals, and metallic oxides called fumes, and gases generated by the heating of the metal being welded, the welding consumables, or any coatings present on the base metal during the welding activities. 90% of these fumes are considered to be respirable. That is, they have an aerodynamic diameter of less than 1 micron. There's over 500,000 workers in the U.S. currently involved with welding and related processes. You'll see on your screen a list of several different types of welding. There's arc welding, shielded metal arc welding, commonly known as stick welding, metal inert gas welding, MIG welding, tungsten inert or TIG welding, plasma arc welding, and submerged arc welding. Each of these welding processes give off different levels of air contaminants. Next, we're going to talk a little bit about the regulations and how to collect air samples. I'll cover OSHA and ACGI standards relative to welding fumes, and we'll also discuss how you can evaluate the air quality within the welding environment. But first, let's look at the OSHA permissible exposure limits. As most of you know, OSHA established the original PELs in the early 1970s. And most of these original PELs were based upon the threshold limit values established by the American Conference of Governmental Industrial Hygienists, the TLVs established by the ACGIH. From the earliest days of OSHA up until 1993, OSHA did have a permissible exposure limit for total welding fumes, and that limit was 5 milligrams per cubic meter of air. However, since 1993, OSHA has been enforcing the exposure limits for each individual metal, the metallic oxide, or the gas, and has not used this PEL for total weld fume. Some of the individual metals that are regulated by OSHA include zinc, which is found on galvanized steel, iron oxide, chromium, which is found on stainless steel, and then aluminum, nickel, and maybe most importantly manganese, which we're going to talk about more in a minute. In 2006, OSHA issued its standard for exposure to hexavalent chromium. That standard is 29 CFR 1910.1026. This standard established a permissible exposure limit of 5 micrograms, and I emphasize it's micrograms per cubic meter, and an action level of 2.5 micrograms per cubic meter. Exposures above the PEL mandate engineering controls, and exposures above the action level mandate that certain administrative controls, including medical surveillance, be initiated. OSHA has also placed exposure to manganese, which comes primarily from welding exposures, on its list of intended regulatory actions. Then in the next slide, we're going to talk a little bit about the ACGIH TLVs. As you know, the ACGIH continues to review its list of TLVs on an annual basis. In 2006, the ACGIH set a new TLV for manganese at 0.2 milligrams, again emphasize milligrams per cubic meter, as total particulate. More recently, in 2009, the ACGIH established a notice of intended change, meaning they were evaluating a change in that TLV down to 0.02 milligrams as respirable particulate. And in this year's edition of the TL book, the ACGIH did indeed adopt this intended change, so the new TLV for manganese is 0.02 milligrams per cubic meter as a respirable particulate. And as we learned earlier, over 90% of the fumes generated from welding activities are less than 1 micron in diameter and are considered to be respirable. Now, next we're going to talk about sampling for welding fumes. Based on a guidance from the OSHA Field Operations Manual, first put out in 1984, OSHA strongly recommends that sampling for welding fumes be done inside of the welding helmet. When welding inside of the helmet, for all practical purposes, precludes the use of any respirable size sampling devices such as miniature cyclones, which are used, for example, when sampling for silica. Therefore, it's often necessary to take multiple samples to characterize an employee's exposure to the welding fumes, the small particles generated during welding, and some of the larger particles that might be generated during grinding activities. As you'll see on the next slide, any properly trained health and safety professional can perform air contaminant monitoring, but it's best to utilize the services of a CIH. By utilizing a CIH to collect, or at the very least to direct the collection of these samples, quality assurance and control can be achieved. You should remember to use only an AIHA accredited laboratory for the analysis of your welding fume samples. And the hygienist should be careful to keep careful records of his or her calibration and sampling procedures. You should also remember that you have an obligation to make the results of your air monitoring available to the employee who was monitored or a designated representative of that employee. To comply with OSHA regulations, companies with welding fume exposures above acceptable levels must develop and implement control strategies. We'll discuss the various options in this section of the presentation. The next slide, you'll see OSHA's hierarchy of controls. These hierarchy of controls should be followed when addressing any air contaminant problem. The control measures are listed in order of their recommended implementation. The first and best remedy is modification or substitution. Secondly are engineering controls, which includes local exhaust ventilation. Third is administrative or work practice controls. And last, and the least best option, is the use of personal protective equipment, such as respirators. At this time, I'll hand it back over to Aaron, who will elaborate on the first control measure, namely process modifications or substitution.
Hello, everyone. Hazard elimination or abatement through process modification or substitution is the first step towards compliance when looking at the hierarchy of controls. In this step, there are a couple of considerations that can be looked at for the weld process. Typically, these are material condition, welding process, shielding gases, filler metals, and weld parameters. Because weld fume is very application specific, welding equipment and filler metals manufacturers must adhere to a standardized fume generation test for comparative purposes. This test method, defined in AWS F1.2, the laboratory method for measuring fume generation rates and total fume emission of welding and allied processes, measures fume generation rates, or FGRs, which is the measurement of total fume by weight per unit time. This is typically expressed in grams per minute or milligrams per minute. This information can also be used to define what is known as percent fume, which is the percentage of the filler metal by weight that is converted to weld fume. The test procedure defined in AWS F1.2 uses a standard fume chamber design as shown in the graphic and follows a few simple steps. A process procedure is welded in the chamber for a given amount of time. A blower pulls the fume through a filter media during welding and after to allow the chamber to clear. And the filter is weighed before and after the test, with the difference being the amount of fume collected. The material condition is one of the most often overlooked options to reduce weld fume. Blasted material is typically preferred. However, switching from hot-rolled to cold-rolled material can offer a benefit as well, since mill scale can have a substantial effect on fume generation rates. The effects of welding on different types of materials are compared in the graphic. Chemicals used on the base material should be removed prior to welding and can have a substantial effect on weld fume. As can be seen in the graphics, rust-preventative greases and oils can have an effect, as well as residual chemicals such as cutting fluids or coolants. Chemicals added prior to welding, such as weldable primers or anti-spatter sprays, can also have an effect. Weld process selection is typically the least flexible option. TIG, or gas tungsten arc welding, produces very little fume, but to substitute for MIG, or gas metal arc welding, would be detrimental to productivity for most manufacturers. As can be seen in the chart, different processes have different FGRs, and this should be a consideration when selecting a new welding process. One thing I want to touch on is I often get asked about gas metal arc welding pulse as a substitute for your standard constant voltage gas metal arc welding to reduce fume. This can reduce fume. However, because of the number of proprietary pulse waveforms used on the market by different manufacturers, and the fact that most pulse processes are now synergic, it may not always be the case, and any benefit should be validated prior to implementation. Shielding gases are typically the simplest change with the most benefit. For the flux core process, mixed gases such as 75% argon, 25% CO2 produce much less fume than 100% CO2. For the GMAW process, switching to a richer argon blend typically offers lower fume. Additions of oxygen or helium have also been shown to reduce fume. As you can see here in this graph, it shows the effect of different gases when used in conjunction with the flux core arc weld process. Filler metals also have a dramatic effect on weld fume, as can be seen here in the emissions characteristics of wires of the same classification can vary drastically from product to product and manufacturer to manufacturer. Weld parameters can also be tailored to reduce weld fume, the most notable setting being voltage, which controls arc length. Typically, shorter arc lengths show reduced fume, so any effort to lower the voltage used in your weld procedure can help reduce fume. As mentioned earlier, amperage also plays a role as well, and it is best to set your amperage towards the top of the operating range of the electrode diameter selected. Process modification or substitution, while effective, may not always be feasible. Changing weld parameters and modifying existing procedures may not fulfill contractual obligations, meet code requirements, and could result in inadequate weld quality, or could be costly to requalify weld procedures and welders. Additional operations such as blasting or changing processes from gas metal arc welding to gas tungsten arc welding, in an extreme example, may add cycle time or cost, and process modification itself may not be enough to ensure compliance. Now I'll hand it over to Al Hilbert for a bit of discussion on engineered solutions.
Thanks, Aaron. So, looking at the OSHA's hierarchy of controls, step 2 in this whole process is engineering controls, and that includes mechanical ventilation, process enclosures, general or ambient ventilation, local exhaust ventilation, otherwise known as source capture. So these are different ways to do engineering controls. Fume extraction guns, process enclosures is a great way to control fume generation or protect the worker from fume generation exposure. There's a lot of ways to do that. You can do that by creating a barrier. Automation cells are a great example. Another way is to use the enclosures on a machine. Sometimes safety guarding can be part of that. Small tanks, pressure vessels on like lathe welders are a great example. When you use them enclosures, it's much easier to capture that fume and filter it. General or ambient ventilation. This is where you use large fans, collectors, sometimes an HVAC system, and basically it's moving large quantities of air to dilute or filter the contaminants based on an air exchange schedule. So depending on the fume generation rate, you may need to turn over that air within a space or the building 2, 3, 4, 5 times an hour. So that's kind of determined by the fume generation rate in the building or in that area. So process enclosure or general ambient ventilation summary, kind of the advantages is really you're removing the smoky haze from the facility when you're doing that ambient system. They're sometimes the only course of action when there's a lot of overhead cranes and obstructions that really make ceiling to floor ducting installation impossible. Sometimes unducted systems can be more flexible when work cells move around frequently within that area, and at times just really less overall noise. Disadvantage, doesn't necessarily protect the worker's breathing zone. So when you have those high overhead air fans and movement, again, it kind of clears out the haze in the building, but when the welder's welding, the smoke is still coming up into his helmet. higher installation costs and higher operating costs depending on what kind of system you have. If you can imagine in the northern areas, if you had to turn the air over within a space or a building 5 times per hour, how much that would cost to reheat that air if it's exhausting outside. So things to keep in mind. And really just less efficient than source capture overall, because once the fume gets up in the air, it's harder to capture it. So local exhaust ventilation, otherwise known as source capture, really this is it's the preferred method under engineering controls. This captures and removes the contaminants right at their source before they reach a breather's working the worker's breathing zone. Again, preferred over general ventilation because you're capturing it right away, and you should be pulling it away from the breathing zone. Available solutions. So this is your portable or wall-mounted stationary fume extraction equipment with an arm on it. Those extraction arms can be connected to centralized collector systems. So that's where a large system can be placed outside or inside the building with ductwork connecting the arms or boom. Sometimes it's a boom with an arm at the end of that boom. High vacuum systems with fume extraction guns is another great way to do it. That's like the ultimate source capture. It's capturing the fume with the fume chamber right in the end of your MIG torch. The larger systems can also have, like a mobile system can have a hose on it with a magnetic hood that can move up into a space up on large equipment where it's kind of hard to get an arm into that area. There's downdraft tables, there's backdraft slotted hoods. There's many different ways to capture, to do local exhaust ventilation. So hood positioning on like a local exhaust ventilation source capture, really you want to have that hood opposite the welder, positioned about 45 degrees angled away so that it's pulling the fume, again, away from the guy's breathing zone. The hood distance will vary depending on the velocity and the volume of air. So it's real important to have good air movement within that system so that you get about 100 feet per second is the velocity that you want to be pulling that away from. As a general rule, it's about the diameter of your hood or 1.5 duct diameters. So if your extraction arm is 8 inches, it may be 12 inches of good extraction. There's some new technologies that can increase that up to 5 feet. So local exhaust ventilation, kind of a summary here. Again, the advantages is that it's capturing the contaminant right before it reaches the worker's breathing zone. Does a real nice job if you're capturing it at the source. Basically, you prevent that smoky haze in your facility, and it is the recommended method by OSHA and ACGIH. Disadvantages, feasibility is questionable on large weldments. So really, when you have a large weldment, it's difficult to keep moving that arm or that local extraction device from spot to spot on those large weldments. Can the extraction hood get close enough so that it can capture the source and be unobstructed? Is the capture velocity enough to pull the fume away from the welder? And is it portable enough to reach all portions of the weld? Administrative or work practice controls, really that's just centered around worker positioning. It's kind of common sense stuff, right? So always keep your head out of the fumes. If a worker is hunched up over the top of that arc, that thermal rise from the fume comes right up into your helmet. And it's just something that welders need to be aware of. We see it quite often where the guy's just right over the top of the weld, and we want to teach them and keep reminding them not to do that. So from here, I'll hand it over to Stephanie, and she's going to cover another control measure by OSHA, personal protective equipment. Thanks.
Thanks, Al. As Al said, we'll cover respirators in this section of the presentation, specifically addressing those found in welding environments. So to give you just a general overview, a respirator is a device that protects the user from inhaling dangerous substances, such as dust, fumes, vapors, or gases. Respirators are recommended for use in the following situations. 1, if engineering or work practice controls are either not feasible or do not lower exposure levels enough. 2, in maintenance or emergency situations. Or 3, during the installation of other fume management solutions. According to OSHA 29 CFR 1910.134, which is the standard dedicated to respiratory protection, only NIOSH certified respirators should be used. One thing to note, all respirators are given an assigned protection factor, which is sometimes referred to as an APF. This number indicates the level of protection that a respirator or class of respirators is expected to provide when the employer implements a respiratory protection program. I'll provide specific examples in the next few slides, but wanted to note that a higher APF usually indicates increased levels of protection. Specifically looking at respirators in welding environments, OSHA has really identified 2 major classes of respirators, one being air purifying and the second is atmosphere supplying. On this slide, we'll talk specifically to air purifying respirators. So air purifying respirators remove contaminants from the air before it reaches the user. There are 2 respirators in this class that are commonly found in welding environments, one being half masks and the second being PAPRs, or powered air purifying respirators. Half-mask respirators are worn underneath the user's welding helmet or grinding shield. They have an assigned protection factor of 10 and contain replaceable filters or cartridges. Half-masks are tight-fitting respirators, meaning they do require a fit test prior to use. In welding applications, make sure to select a low-profile half-mask respirator that is designed to fit underneath a welding helmet. Another example of an air purifying respirator is a PAPR. These respirators, when paired with the welding helmet, have an assigned protection factor of 25. They use a belt-mounted, battery-powered fan to pull ambient air through a set of filters, sending filtered air through a breathing tube to the user's sealed helmet. PAPRs are considered loose-fitting respirators, meaning no fit test is required. The second class of respirators are atmosphere-supplying respirators. They provide clean, breathable air from an uncontaminated source. Specific to welding environments, supplied air respirators are sometimes used. These types of respirators rely on compressed air from a stationary source being pushed through a hose to a belt-mounted air control device, then sent through a breathing tube to the user's sealed helmet. Supplied air respirators, when paired with a welding helmet, have an assigned protection factor of 25 and are considered loose-fitting respirators, so again, no fit test is required. Some supplied air respirators have the ability to cool or heat the air that is delivered to the user. So now that we have a general understanding of when to use respirators in those common in welding environments, some of you might be questioning what respiratory option is suitable for your needs. So to make this determination, a basic calculation can be done using the following elements. 1, actual exposure levels of regulated metals in your environment, and this can be determined through air sampling. 2, permissible exposure limits of metals relative to your air sampling, which can be found in OSHA 29 CFR 1910.1000 Table Z-1. And 3, assigned protection factors of the respiratory options you're considering. Once you have these pieces of data, you can determine what respirator is appropriate for your application by calculating the maximum use concentration, or MUC. To determine the MUC, you multiply the respirator's APF by the chemical's OSHA PEL. The MUC is then compared to actual air sampling results to determine the proper respirator. We'll quickly walk through an example of how this is done for your reference, but note that an industrial hygienist can assist in this process. For this example, let's assume air sampling exposures for hexavalent chromium came in at 65 micrograms per square meter. We aren't sure whether to have employees use a half mask or PAPR in this instance, so it's a good idea to go through and calculate the MUC for both a half mask and a PAPR. So the first example you can see, with an APF of 10 and hexavalent chromium PEL of 5 micrograms per square meter, you can see the MUC for a half mask in this situation is 50. In the case of a PAPR, you can see the MUC is 125. Comparing the MUCs of 50 and 125 to our air sampling exposure of 65, it can be concluded that a PAPR would provide appropriate protection in this example. Now, as you can see on this slide, OSHA does consider the MUC to be the upper limit at which the class of respirators is expected to provide protection. So whenever air sampling exposures approach that MUC level, the next higher class of respirators should be chosen. For companies deciding to use respirators, they must create a written respiratory protection program, again per OSHA's 29 CFR 1910.134. And it should cover the following: selection of respirators, medical evaluations, fit testing, use of respirators in emergency situations, maintenance and care of respirators, training, as well as program evaluation and record keeping. It is important to note that a written respiratory protection program is necessary in both voluntary and mandatory situations, with voluntary use requiring a limited program. So to summarize, here are a few advantages and disadvantages of respirators. Respirator advantages: the respirators deliver filtered air directly to the user's breathing zone. The constant air movement associated with PAPRs and supplied air respirators offer users heat stress relief, and that constant air movement also can eliminate some of the fogging of safety glasses and helmet lenses. And lastly, respirators provide users unlimited mobility. A few disadvantages of respirators: they do require a written respiratory protection program. So although these programs do take time to create, once established, they can be easily modified for future applications. Respirator users must be medically evaluated and in some instances fit tested. Respirators only work properly if used correctly, meaning the effectiveness and burden is placed in the hands of the respirator user. If employees are open to respirator use, then this usually is not an issue. But for those more skeptical, this could become problematic. And lastly, the cost of filters and other consumables can add up over time. In conclusion, I'm going to pass it off to Bert for a few closing thoughts.
Remember that weld fume management is an ongoing process. Welding fume levels need to be retested anytime there is a workplace change. By OSHA definitions, these changes may include alterations in the production process, a change in raw materials, such as switching to stainless steel or galvanized metals, a change or use of different welding equipment, new personnel, or different work practices or control methods used in the workplace. That's it. I think it's time for questions.
All right, great. Thank you, everyone. That was a fantastic presentation. Before we go into the Q&A, I want to remind everyone of the short evaluation survey I mentioned at the beginning of the presentation. It should be appearing on your screen now, and we just ask that you consider completing it to let us know your thoughts. Your input is important as it helps improve future webcasts. So please do take the time to fill out the survey. If you don't see the evaluation survey popping up on your screen, please make sure your pop-up blockers are turned off. All right, now let's dive into some questions. I'm going to start with Al. There are a couple questions related to some of the things that you spoke about, and I wanted to start with a question regarding shielding gas. Does capture at the gun interfere with shielding gas?
Thank you. Great question. It can, to be short on my answer. There's a couple things that go into play here. So generally, you have to turn up your shielding gas, the flow, the CFH. You have to push it up about 3 to 5 CFH on your shielding gas to help overcome that. when you get into tight corners with that fume gun, it can, with that suction at the end of that fume chamber, it can pull away the shielding gas. So there's adjustments. Some guns have adjustments to open up a port to bleed off the pull. There's different techniques, but it's definitely a concern, and it's something you have to watch out for, yes.
Okay, great. And another question for you, Al, again, is can someone filter and recycle air in a general air movement system?
Absolutely. So it's pretty common in these large systems when they're recirculating inside a building to just pull that air in and recycle it. Obviously, you want to still have a good filter so that when you're recirculating that air, making sure that you have a high-efficiency filter of some sort so that you're not just relocating the fume back in the air.
Okay, great. Bert, I had a question for you. You mentioned at the beginning of your presentation that OSHA recommends sampling from inside a weld helmet. What about for welders who wear something like an AdFlow welding helmet respirator? What about that?
Again, an excellent question. And OSHA also stipulates that you shouldn't break the barrier of any employee who's wearing a respirator. In other words, you can't put your sampling device underneath a respirator, a tight-fitting respirator. You don't want to break that seal and increase the harm to the employee. So sometimes you have to get pretty creative. It's best to place the filter as close as you can to, if you can't get it underneath the helmet, I typically place the filter by an individual's Adam apple so that when he flips the welding helmet down, the bottom edge of the helmet will typically cover a person's Adam's apple. So I would clip it to his shirt collar by his Adam's apple.
Okay, great, Bert. Aaron, you talked a little bit about manganese. Is there a good alternative to manganese in the welding rods or wire to eliminate the exposure?
Well, that's a tough one because manganese is an essential strengthening and toughness ingredient in steels. However, there's kind of two different ways you can go down this. Manganese in the weld fume, manganese exposure is kind of a balancing act between percentage of manganese in the weld fume as well as the total amount of your weld fume. So there's two different ways that welding consumable manufacturers have come up with to combat this. And one is low fume wires, which just address the total fume. And some manufacturers are now coming out with low manganese alternative wires. And those have shown to reduce manganese in the weld fume by 60 to 80%. But with that being said, they don't necessarily decrease the total amount of weld fume, just the amount of manganese in there. Hopefully that answered the question.
Great, thank you, Aaron. Al, what is you mentioned a little bit new source capture technology. Can you talk a little bit more about this new source capture technology that increases the extended capture distance?
Sure, certainly. So this is something very new. It's something we're calling zone flow. Basically, we've developed a way to source capture weld fume at a greater distance, and we're doing this by creating a low pressure zone in front of the typical 18-inch, about that 18-inch capture area. So basically, this draws fume in that zone up to about 5 feet away, and still providing that source capture with the added benefit of little or no arm movements. Again, still gives protection with minimal or no interaction by the welder. So it's pretty cool design.
Okay, great. Bert, I want to come back to you for a couple questions. What is the best solution for protecting welders in tight, confined space atmospheres, especially if it can be difficult to acquire PPE due to space limitations?
Well, as a matter of fact, I'm working with a company with exactly that situation. A welder has to crawl into a tunnel, if you will, and it's very difficult, frankly. You either have to rely on some of the new technology, the new source capture ventilation like Al was talking, which will increase the capture distance. If you place that at the edge of the confined area, it can help to draw the fumes away. And some of the respirators do fit underneath the welding helmet, not the PAPR, but some of the smaller air purifying respirators can fit under a welding helmet. That's the best situation. Last but probably least, you may have to go to some job rotation and limit the welder's exposure based on his time welding.
Okay, great, Bert. I want to ask you another question, and this is to do with sampling. I'm just going to read the question straight as how it was submitted. This individual has been asked several times by their clients to do air sampling to evaluate welding fume exposure. However, these clients don't weld very much, and they only do so for short periods of time, and that makes it difficult to meet the minimum sampling duration and volumes. Do you have any guidance or suggestions for sampling in situations like this where clients may not, weld a whole lot?
Well, a very common situation, and a welder typically spends a great deal of time on setup. Then he may weld for a while. Then he might do some grinding. Keep in mind that all of these exposure limits we're referencing are based on an 8-hour exposure. So my advice would be to sample for the entire work shift, up to 8 hours if you can. And then in your notes, just specify how much time the welder spent at each activity, setup, welding, grinding, or other activities. Remember, it's an 8-hour exposure, so even if he's welding for an hour or less, the same limits would apply. So go ahead and sample for the full shift, and then base your engineering controls on the outcome of those results.
Okay, great. Thank you, Bert. Now, Al, how is the spent material captured by the source collection system treated under waste treatment regulations? For persons handling these waste contained in the source collection system, what precautions should be taken since the contaminants are now a solid and not a fume?
Right. So the best way to handle that is work with your waste hauler, whoever picks up your waste. You would work with them. Basically, the particulate that's collected on the filter, and I say it that way because the filter by itself is clean and can be disposed of. Once you start collecting particulate on it and maybe pulse cleaning it off, so now you have that particulate falling down into some kind of collection container. That particulate needs to get a waste profile. So a waste profile is attained by sending a sample in to a lab. Again, work with your waste handler. They can probably suggest a lab in your area, but it's called a T-clip test. And to kind of boil it down to make it simple to understand, it basically it determines how soluble that waste is and if it can leach into the groundwater. So depending on that waste profile, the waste handler would put it in a section of the landfill that is suitable for that profile. So I can't answer the question. I can't tell anybody to throw it away because I don't know what it is. So you got to work with your state, local guidelines.
Okay, great. Thank you. And Bert, we just want to clarify something real quick. Regarding the sampling for weld fume contaminants, it is inside the hood or apparatus being worn, correct? That's the intended location. The exception would be kind of a respirator that requires a tight seal.
Right. You don't want to break that seal. Correct.
Okay, great. All right. We still have a bunch of questions, but if there are some folks who do want to ask a question, I just want to give you a reminder. It's in the text box located on the lower left-hand corner of your screen. You can just feel free to type it at any time and click Submit Question. I want to go through some of these. Here's another one right here. Al, for hood capture distance that's 12 to 18 inches, can you make recommendations for a closer distance? For example, 100 FPM at 6 inches or 9 inches from the source?
Well, the capture velocity, that 100 feet per minute, is what OSHA recommends so that it can actually capture it and be pulled into an extractor. There's different types of systems. So, I was talking about a hood at 12 to 18 inches. I was referring to high volume, low vacuum systems. Think of larger ductwork like the ductwork in your house for your heating, ventilation, right? There's also high vacuum systems, which, just as it sounds, can be like a vacuum cleaner with the smaller hoses, but it's got a lot more suction, less volume. So those systems there is typically a smaller or a shorter capture distance because there's less volume of air being pulled in. So hopefully I'm answering that question right. But again, if you look at the duct diameter or the hose diameter, it's generally about 1.5 times or about the width of your hood. So on some of those high vac systems, for instance, they have like a flexible funnel nozzle, and that nozzle itself may be 3, 4, 5 inches wide. And again, in general, that's about your capture distance.
Okay.
I hope that answered that question.
Great, thank you. Aaron, I want to go to you with a quick question. What type of fume reduction can be expected from conversion to a low fume or low manganese wire?
Typically we've seen in the 60 to 80% range. It's going to vary. The weld process itself, your welding procedure plays a big role in the fume generation and also the components of that fume, one of which being manganese. So at different points on an amperage range, it's going to vary. But typically switching, you'll see a 60 to 80% decrease. So typically what we've seen specifically with the flux core processes is that it ranges in the 6 to 10% of the total weld fume is manganese, but with these low fume electrodes, low manganese flux core electrodes, we're seeing typically 1.5 to 3% of the total weld fume is manganese.
Okay, great, Aaron. And Stephanie, I want to bring up a comment from one of our listeners today regarding PAPRs with an APF of 25. You mentioned PAPRs have an APF of 25, but this individual, brings up how that's only for loose-fitting face pieces. Are there APFs that have kind of a tighter seal that might have a higher APF?
Definitely, there are. When I mentioned the loose-fitting face pieces, such as the PAPR systems with a welding helmet having an APF of 25, that's appropriate for respirators used in welding environments. Oftentimes, you'll see users with full face respirators connected to a PAPR blower assembly as well, and those APFs can be higher, but typically in welding environments, because you do need that a certain shaded lens to perform your task, we don't see those as often. So again, in this presentation, just sticking more toward respirators that you would see typical in welding applications.
Okay, great. Thank you. Bert, I have another question for you regarding IH sampling for 8 hours. The person who submitted this question, they do their sampling for 8 hours, but the employees are concerned that they sometimes work 10-hour shifts and wanted to know why sampling isn't done for 10 hours. Can this individual take the 8-hour sampling and extrapolate it out for 10 hours, or should they do 10 hours worth of sampling?
Well, that's, again, an excellent question. And due to practical reasons, it's sometimes difficult to sample for a full shift. It's indeed even hard to get a full 8 hours because you have setup time. The way I would answer it is this: if the activities are constant, if there's little change in the activities, if the person is doing the same type of welding all day long, yes, certainly you can take a 4, 6, 7, 8 hour sample, and you can assume that that exposure level would be the same for a full 10-hour shift. If the activities are highly variable, obviously you can't do that. There is a convention for longer work shifts. It's not OSHA regulation, but there is a convention in the industrial hygiene community to adjust permissible exposure levels down for extended work shifts. Okay?
Okay, great. We have another question for Aaron here. do GTAW process yield a lower fume exposure than that of GMAW or SMAW weld processes?
Yes, the gas tungsten arc weld process will yield a much lower fume exposure than the GMAW or shielded metal arc weld process. It's a more stable process, but the other half of that coin, the flip side of that coin, is that it's a much lower productivity process. So I think somewhere in the range of 80% of your weld fume is generated from your filler metal. Because you're depositing so much more filler metal with the GMAW and SMAW processes, you're going to generate a lot more fume than you do with the gas tungsten arc weld process.
Okay, great. Bert, with air-supplied respirator systems, how often do you need to check the grade D breathing air?
Oh boy, off the top of my head, I'd have to check the OSHA regulations. I believe, well, certainly at a minimum once a year. It may be more often than that. I would go to the OSHA standards, which you can do online, of course, and check. But certainly once a year, a prudent course might be to do it more often, but I don't know off the top of my head what the standard calls for.
Okay, great. It's always good to double check what the OSHA standard says. So.
Yeah.
Al, I want to ask about air pollution issues. Do those exist with ventilating extracted weld fume to the atmosphere?
There are,
with a high wall next to the exit or with a ceiling.
So are we referring to like the EPA standards when you say exhausting? I'm sorry?
Well, are there air pollution issues with venting extracted weld fume into the atmosphere, be it either inside or outside of the building? I'm assuming this individual is talking about outside.
Well, so if we're talking about outside, there are some newer standards by EPA. If your business is classified as such that one of your primary functions is welding, and if you're using over 2,000 pounds of rod or wire a year, you may fall into that classification. That's something you would want to check your NAIC codes to make sure that you fall under that classification. But yes, it's getting more and more where you would need to filter that air for weld fume. Manganese, nickel, the few other higher identified materials can't just be dumped outside anymore. Basically, they're saying that you can't just throw it in the rivers and pollute on your neighbors. If you're going to exhaust outside, you should be filtering that air as well. So there are some new standards with EPA, yes. Okay,
great. And can you, Al, discuss the validity of claims that the welding zone can't be disrupted by exhaust currents? Which welding processes are not disrupted by LEV?
So for sure, like subarc is basically covered with the flux, so that's never an issue there. Flux cord welding, or self-shielded, or stick welding, those are typically used outside for just that reason. When you start getting into coverage gases, that's when fans, drafts, open doors, windows, when the air movement is greater than, I'll say, 250 feet per minute, and Aaron, maybe you can back me up on this one, but when you start getting into that higher velocity of wind speed by the arc itself, it can start disrupting shielding glass. Aaron, any further comments on that?
No, I think you covered it pretty well.
Okay.
I'm sorry, go ahead.
Well, I was going to say, when you start getting into the TIG and maybe when you're doing aluminum, it can be a little bit more sensitive. So as you get into the processes that are just more sensitive to that air movement has to be reduced or blocked, or you need to be aware of it.
Okay, great. Thank you. Bert, we have an individual here who asked a question regarding dealing with welding and oil. So when dealing with heavy oil on the metal that you're welding, it seems like this creates more fumes from the welder. Will this issue deter what kind of respirator a welder would be looking for in the case of the respirator not being able to filter?
No, the respirator should be able to protect against anything generated from oils. The oils that might be on the surfaces, first of all, as we pointed out in our presentation, it's best to clean the surface as much as possible before any welding is done. But for any residual oils or grease that's left on, respiratory protection should adequately control those. The things we're really worried about are the metallic fumes generated primarily from the filler metals, as we've talked about, and the particulates generated from the burning of the grease or oils would be really less hazardous.
Okay, great. And one last question for you. Is it true that a complete medical surveillance, PFT, and fit test is needed even if a respirator is for voluntary use and Appendix D needs to be completed? Is that the case?
Medical surveillance is required even under voluntary usage because the act of wearing a respirator itself does cause stress to the heart and lungs. So medical surveillance in all situations. However, fit testing is not required in a voluntary situation. Not required fit testing, just medical surveillance.
Okay, great. Thank you. And we just have time for one last question. We've had a lot, so I want to thank everyone who submitted questions, and I apologize to everyone whose question we didn't get to. My last question here is going to be for Al. Can you elaborate just a little bit more on large and hard-to-reach spaces, such as inside of a tank?
Sure. So on these hard-to-reach spaces, specifically inside of a tank, sometimes they use exhaust equipment to just simply exhaust and pull that air out of the tank. Considerations, whether it's a restricted space or a confined space, has to be taken into account. If it's confined, then there's other OSHA rules that you need to follow. Having a watcher, have some guy watch the guy inside the tank. But in relation to fume extraction, things you don't want to do is short circuit the welder, and what I mean by that is consider the airflow through the tank. So there should be one side of the tank where the air is coming in, and then another side of the tank where it's being pulled out. And what you don't want to do is have the welder in between the weld process and the exhaust. That's basically short circuiting, so that fume is going right past him. Local exhaust ventilation, the nice thing about getting some in there, in addition to if you need dilution and ventilation, is that it allows the welder to see what he's doing a lot better. It doesn't allow that fume to accumulate inside the tank. So if you can extract it right away, again, it's almost like the same thing inside a big building. If you can extract it right away at the source, it captures it and pulls it out before it can get up in the air and fill that space.
Okay, great, Al. Thank you, and thank you to everybody. Again, I apologize. We're running out of time, and we didn't get to everyone's questions, and there were a lot of them, but rest assured all of these unanswered questions will be forwarded on to our speakers to respond to. Once again, I hope you take the time to fill out the evaluation survey on your screen to give us your feedback. And with that will end today's Safety and Health webcast. I'd like to thank Bert, Al, Stephanie, Aaron, Miller Electric, and Holbert Brothers Company, and all of you who listened in. Thank you, and have a great day.